All right, let's start. Good morning. How was the midterm? How do you feel about it? Okay, generally speaking. What did you guys say to the averaging problem? If a sequence converges, then the time averages converge also, and vice versa. So, if you have a sequence that converges to something, then is this equivalent to saying that the time averages, this is the sort of time average until time n, say 1 to n, converges to this. What did you guys say? No? So there's this direction and there's this direction. How many of you said yes to this? How many of you said yes to this? Yeah, I mean, the true answer to this is correct and this is false, actually. So if something converges, it converges on average, but not vice versa. So for instance, if you had -1 to the n, this is an oscillating sequence. It doesn't converge, but the time averages converges to 0. So on average, this is just 0. Yeah, don't worry, though. After the midterm, I sort of realized maybe writing the statements or proofs for these might be a little bit too complicated. This was a problem that I had used last time I taught this course in a problem set. So I recycled it. So we'll see. Depending on the performance, I might be extra lenient about this. Generally speaking, I don't think you should be too worried about the grades. I tend to grade very leniently, but you'll see, of course. People say this, and then you receive a score that you don't expect, and so on. Anyway, so we have a couple of things to discuss still about continuity, continuous functions, and so on. We still need to talk about different notions in which one can think about a sequence of functions converging to something. There are many, in fact, but there are many notions of sequences of functions converging, which we're going to sort of discover as time goes by. But the two most important ones are pointwise convergence and uniform convergence. And once we're done with that, we're going to switch over to integral calculus, and we're really going to focus on this other textbook by Fonda. We're going to take a break from the Taylor textbook. Okay, so we were discussing the proof of this theorem. I wrote this in full, but we pretty much did most of it. There's this harder part 2, which I'm going to cover now. But let me just restate. I have a closed and bounded interval, or in the terminology of problem set 4, if you want, a compact interval, lambda to rho, and I have some function on it taking real values. And you see, this is sort of the benefit of notation as well. You can really compress what you're writing. Economy of symbols and so on. Then I have 3 items. First, and these are all about like 3 properties. One of them is continuity. You see continuity shows up. The other one is strict increasing or strict decreasing property, so monotonicity. And the third is whether or not the image of the function is a closed and bounded interval itself. And so that's why I'm sort of lumping these together. In the textbook, these are different, separate sort of theorems. But I find it much easier to remember these if I lump them together. So the first one says, if you have a continuous function, so if your function is continuous, then the image, in fact, is the closed and bounded interval from min of f to the max of f, which exists as numbers. Second says, if the image of your function is some closed and bounded interval, and f is strictly increasing or strictly decreasing, then f is continuous, which in principle means if you were to combine this with this, in this kind of a situation, L will be the min. So you can just combine them. Because if you have 2, you have continuity, which means that you can combine it with this to figure out that min has to be L and max has to be R, and so on. And then the third says if you have a continuous function and if f is strictly increasing or decreasing, then in fact f inverse as a function exists and it has to be continuous. And we already proved 1 and we already proved 3, assuming 2. And I told you 2 is the harder one, harder part, and that's what we're going to finish proving. And so I'm just going to focus on the strictly increasing case. The strictly decreasing case is pretty much the same. Suppose the image of f is some closed and bounded interval, and suppose f is strictly increasing. Okay, I'm assuming the hypotheses, this and this, but I'm going to go for a contradiction, and therefore I'm assuming that even though the hypotheses are satisfied, the conclusion is not. Okay, I didn't say it explicitly, but I'm going for a contradiction here. What does this mean? What does it mean for f to be not continuous? Well, that means that f is discontinuous, or in other words, it fails to be continuous at least one point, okay? Which means that there is some x star in I, such that there is some sequence, x bullet, that converges to x star, but the image sequence, f of x bullet, does not converge to f of x star. Okay, I just negated what it means for a function to be continuous everywhere. And then now I want to turn this into something more actionable. And so I open up the definition. I have a bunch of quantifiers and so on. But the point is that when I turn this into a logical statement, f of x bullet does not converge to f of x star, that says this. There is some there's an epsilon 0, positive, such that for any time n, capital N, there is some lowercase n after this capital N, such that f of x sub n is more than f of x bullet, more than epsilon 0 apart from the target f of x star. Now, so this is sort of like a common traditional thing. In this case, because this epsilon I want to keep fixed, people would sort of like put a 0 or something. So when people use epsilon, this is not necessary, of course, putting this subscript 0, but just to sort of remind themselves, a lot of people would use a slightly different notation. They wouldn't just leave it as epsilon, because epsilon should be some arbitrarily small number. Question? Oh, OK. So this is just like a notational thing. OK. Ultimately, these epsilons and n's and all that stuff are dummy variables. And if you so choose, you could use different letters for these. But somehow, for me, for instance, I have a psychological attachment. So when I think about sequences, I think about lowercase n's and uppercase n's and so on. OK. Now, from this, I can farm this statement, OK, and come up with a subsequence of x bullets such that f of x bullet is always farther away from f of x star. So this says, so let's just draw the picture. Okay, something like this. Let's say this is your epsilon 0. Something like this. For capital N equals 1, the statement, the red statement says there is some time after capital N equals 1 such that f of x sub n falls out of the epsilon 0 ball. Okay? And so there's an n sub 1 after this capital sub n such that x sub n sub 1 is away from the target. Then what I can do is I can choose n, capital N, to be lowercase n sub 1 plus 1, which would then give me that there's a time after this, farming again, such that, so maybe in between it comes in inside this ball, but I know that there is some time after n sub 1 such that the n sub 2, n sub second term falls out of this epsilon 0 ball and so on. And so forming it like this, I get to come up with a sequence that I know always stays outside this epsilon 0 ball. So forming, there is a j, let's say, such that x bullet composed with j, the subsequence, let's call it x bullet prime, is a sequence, well, is a subsequence of x bullets such that x bullet prime, well, x bullet already converges to x star, so this subsequence too has to converge to the same thing. But I now have the stronger statement that for any time n, f of x sub n prime is indeed more than epsilon 0 away from f of x star. So you see, by sampling out a subsequence, I took this and turned it into a stronger statement. Now I am guaranteed that if I just look at these times given by the j function, I'm always going to be farther away from this marked target. Again, I will leave this to you as an exercise. If this is not clear, this is a good exercise. So really, when I write it like this, I really mean the subsequence function, or rather the strictly increasing function j, is defined so that j of 1 is n sub 1, j of 2 is n sub 2, and so on. And so the reason why I choose these like this is so that I have j strictly increasing. OK. I'll leave this. And in fact, let's draw a picture here as well. So this is lambda, this is rho, so that this is my I interval. This is L, this is R, this is my image interval. And I assume that f is strictly increasing, which means that its graph has to pass through these 2 points. And I chose one horizontal x star. F has to pass through something here. So let's say it's like this. This is f of x star. Now I have some epsilon 0. OK. So this is 2 epsilon 0 in width. And then I have some sequence here that converges to x star. Okay, maybe jumps this way, goes back, and so on. I'm kind of stuck. Maybe I should ask you, what can we do now? Remember, this is what we're trying to prove. Item 2. When you're stuck during a proof, what you can do, again, let me reiterate, you go back to the statement and try to figure out which assumptions you haven't used so far. So we have this. We haven't used the fact that the image of f is a closed and bounded interval. We haven't used the fact that f is strictly increasing. We only used the fact that f is not continuous. Well, using this is slightly harder. I want to somehow use the fact that f is strictly increasing. What I can do is I can sample out a further subsequence so that this sequence that initially possibly jumps all around is strictly increasing. Okay. So first of all, I know that once I passed over to the subsequence, none of these terms is going to be exactly x star, because otherwise f of x prime sub n would be exactly f of x star. So we have that for any n, the nth term of this subsequence I sampled out is at a distinct horizontal compared to x star. Then what I can say is this. As this x bullet prime sort of like converges to x star, well, either for infinitely many times it's going to hit the left-hand side, or it's going to hit infinitely many times the right-hand side. I kind of use this same trick in the nested interval property. It cannot be the case that it hits the left-hand side finitely many times and the right-hand side finitely many times also. So either the number of times such that x sub n prime is to the left of the target is infinity, or the other way around. Okay, that's with a prime. So I'm hitting either the left-hand side infinitely often or the right-hand side infinitely often. Maybe both can happen. Maybe this happens. Doesn't matter. All I need is one. The point is, without loss of generality, I can assume that the first thing happens. And based on this, I can further sample out a subsequence of x bullet prime to get x bullet double prime, say, that I know is guaranteed to be always to the left. Then, so without loss of generality, say the first happens. Then there is a k such that x double prime, which is x prime composed with k, this is a further subsequence now, is a subsequence of x bullet such that, well, first it converges to the original point. It has this property and this. So you see, I started with some sequence that has some properties, and then now I'm sort of sampling out subsequences in composite fashion to obtain more and more properties that I can use. Okay. So I sampled out a times, infinitely many times, such that instead of now jumping around, I have the subsequence that converges to this, but it still might be jumping around here. Okay, so maybe it goes like this and so on. But then I can further take a subsequence of this so as to guarantee that I have strict increasing property. So JKL such that x triple prime is a subsequence of x bullet. It has this property, this property, this property, and it is strictly increasing. X triple prime bullet still converges to the original x star. For any n, it stays away, or rather its image stays away from this f of x star. It's always to the left of my target. And in fact, I can write it like this. It is strictly increasing, so that if I increase the index by 1, it strictly increases. So I started with an anonymous sequence explicit that converged. That was the only property it had, to some point x star. Then I kept taking subsequences of it, and I ensured that this specific subsequence has further properties. I'm going to leave it as an exercise to write these subsequence functions more explicitly to you. Okay. More explicitly. Any comments or questions so far? So now, my picture is very nice. Okay? Instead of looking at x bullet, if I were to look at x triple prime bullet, this is a beautiful sequence that starts somewhere here, and it is very orderly. Okay? Always goes this way. In time. Now, given this, what can I say about x triple prime bullets? Or maybe its image under F. Because you see, since I know that as time progresses, x triple prime always increases strictly, I can use that in tandem with the strict increasing property of F, which would tell me that f of x triple prime bullet would be a sequence that is strictly increasing in the image. Okay, so I would look at this. Maybe something like this. This is how the image would look like, because f is strictly increasing. That was the whole point of sampling out this specific subsequence. I needed a strictly increasing sequence so as to be able to use it in tandem with the fact that f is strictly increasing. Okay, and that's what I'm going to do. I'll continue from here. To be more explicit, in fact, what I can say is this. So let's just turn this into an orange box. Put a star. By orange star, since f is strictly increasing, we have that for any n, I have this. Right? Because if I were to apply to these these two inequalities, f of x triple prime n would be strictly less than f of x triple prime n plus 1, which itself would be strictly less than f of x star. Okay. Now, So now this is a vertical sequence. I'm looking at sequence over here. But it doesn't matter really, because this is a sequence of numbers that is strictly increasing. And I know I can say something about sequences of numbers that are monotonous. What can I say? One of the three theorems about sequences that we discussed. This sequence is strictly increasing. It's also bounded, for instance, bounded by this. I should be able to say something about it.
Isn't the monotonic convergence theorem states that if it's monotonic, it must converge?
Exactly.
Converges. Can't remember exactly where it converges.
To its soup.
Okay, it's the soup.
Yes. So this is a strictly increasing sequence of real numbers, which by MCT, monotone convergence theorem, has to converge to the soup. But since these are bounded, I also know that the soup is a real number. That is, at most, f of x star. Okay? By monotone convergence theorem, limit as n goes to infinity of f of x triple prime sub n exists. It is the soup of these terms. And since f of x star is an upper bound for these terms, in fact, I can write it like so also. Okay. Any comments or questions about this? I use the monotone convergence theorem here. For monotone convergence theorem, I didn't really need strict increasing property here, but certainly if I have strict increasing, I also have non-decreasing. And so that suffices. So I have this. Okay. Well, at this point, what I can say is I can try pushing this further. What should happen, I could say, what could happen is if the soup is strictly less than f of x star. So say there's a gap. And in fact, by this property, I know that instead of writing it like this, I could have written it like this. By this. Let's use dagger, green dagger. So the soup exists. And you see, when I take this limit, the limiting height cannot be within this blue band by construction. This is forbidden, okay? You're not going to be able to reach any height within this small band. I did all these shenanigans just so that I can guarantee this. Okay? So this limit, the vertical limit, has to be somewhere here at most. But then the final hypothesis comes into play, namely that the image of f is everything. Meaning, well, I can take whatever this limit is and take the average of it with f of x star, say here. There has to be some x value such that f of x is exactly at this height, but that cannot happen. Okay, I'll erase the statement. Okay, put a star here. I'm going to continue from star. Let me call this soup, say alpha. Yeah, I can just take the average of these two. So the average of alpha and f of x star this is in the image, which I know is a closed and bounded interval by hypothesis. So so I'll write it like this. So there's an x dagger, let's say, in I, such that f of x dagger is exactly this average. But then again, by the strict increasing property of f, on the one hand, this has to be, so by strict increasing property, nature of f, for any n, x sub n triple prime is to the left of x sub dagger, which itself is to the left of x star. This cannot happen because this converges to this. And finally, we're done. Oh, it's a heavy proof, not an easy proof. But that's why we proved it. So now you get to use it. And now that we have the third theorem as well, you can safely use this idea that continuous functions are those that you can draw the graphs of without lifting the marker off the board. Okay. Any comments or questions about this? Like I said, I realize this is a complicated proof. It's probably the most complicated proof we've ever seen so far, in fact. Yeah. Lots of moving parts. We keep using the hypotheses in multiple ways. You may want to have a look at the proof in the textbook. In the textbook, instead of using sequences, they use epsilons. So maybe that's going to be easier to sort of parse. But the idea is the same. I like sequences quite a bit more, partially because they sort of like discretize the time for me. And so I can say time 1, time 2, time 3 in my mind. And also with sequences of numbers, it's OK. But when you switch over to sequences of functions too, you really sort of start feeling the benefit of thinking about sequences, as opposed to epsilons and deltas. OK, so that's that. We get to use this. This is another technology that we get to use without worrying too much about these matters. OK, so I want to transition to different notions of continuity, different notions of convergence for sequences of functions. But even before that, I need to say a couple words about a property that is stronger than continuity for functions. I'm not going to spend too much time on this, because somehow the terminology for it is somewhat unfortunate. I think it makes things more confusing. But in a sense, the reason why I'm going to sort of keep this next thing minimal is essentially the same reason why I didn't go too much into Cauchy sequences. Yeah, go ahead.
These theorems that we just went over, do they have a name?
No. This one doesn't. I don't think it has a name. Not in the textbook for sure. That's a good question. Yeah. I don't know a name. to me, I think of it as the theorem that sort of connects monotonicity, continuity, and the image being an interval. These are like three different things. Yeah. There might be a name somewhere out there. You may want to sort of ask ChatGPT or something. Our textbook is, as far as I'm concerned, not doing a great job at giving names to theorems in general, too. Just like states the theorems without telling them what they are called, typically. So that's why I try to sort of supplement it a little bit. But yeah. OK. Any other questions or comments? Yes?
Yeah, you summarized 3 items, right?
Yes.
On the assumption of the domain is...
It's a closed and bounded interval, and f is a function defined on it taking real values.
It's a domain is closed bounded interval?
Yes.
And function what?
The function, there's a function that is defined on it taking real values.
Oh, okay.
Yes.
So what about if it's open the boundary?
Well, not necessarily. That's a good question, but even the first item fails because if you have an open and bounded interval, if you were to imagine something like f of x equals 1 over x, the max need not exist.
Oh, but okay, so max is the output value, right?
Yes.
So you define it, the image is through a specific R?
What do you mean?
I mean, the domain has to be closed bounded.
Yes.
And a function that is in R
That takes real values, yes.
takes a real value.
Yes. So it goes from the interval to the reals in general.
And that real is not extended real.
No. Yes. Very good. Although, even with extended reals, you could have come up with a version of this statement. That's not a major issue, actually. I just wrote it this way because it is more convenient this way. Yeah. Because certainly, you may want to think about functions like arctangents. Then probably, instead of getting rid of I being a closed and bounded interval, you would still keep I to be a closed and bounded interval, but you would allow positive and minus infinity to be values. So imagine something like this. This is like an arctangent type of a thing. So you would want to think of this as what is like a function on this closed and bounded interval, but it actually takes the positive infinity and negative infinity. Pretty much all arguments are going to still work for something like this, like an arctangent type of a function, like a translation of arctangent, I think that this is. But the way I stated turns out to be more convenient for us. Yeah. OK. So any other comments or questions about these? So this property that is stronger than continuity is, it's called uniform continuity. But even before that, I'll put a warning here, or warning or remark. While you can think about continuity in the sort of abstract metric space situation, or in the case of open intervals, whatever, for continuity, because the maximum principle is so useful, the fact that on a closed and bounded interval, a continuous function is bounded, or it has its max and min. When you're using continuous functions, you always want to restrict your attention, or restrict the function, on a closed and bounded interval. So continuity really works with compact intervals. Okay. The same thing is going to happen with integral calculus. When we're trying to do integral calculus, we're going to, if time permits, we're going to talk about improper integrals and so on. But your intuition should be, oh, if I have a continuous function or if I have an integrable function, first I want to sort of think of what is happening on a closed and bounded interval. If your function is not defined on a closed and bounded interval, maybe there are asymptotes and stuff like that, that means that you have to be very careful from the get-go. For differential calculus, it's going to be the other way around, surprisingly. For those of you who have taken differential equations, the reason why in the context of differential calculus you want to use open intervals is because you want to get rid of things like the boundary conditions. Boundary conditions, if you know differential equations, make things work in a sense, but at the same time make things more complicated. But for now, you really want to focus on compact intervals when it comes to continuity, even though, in principle, you can think about continuity in the context of non-compact intervals. And so that's why I'm able to bypass this next property and just mention it. So, theorem. Well, let me first give a definition. I'll write the theorem first. It's better. Because somehow, like I said, this property is called uniform continuity, but there's also uniform convergence, which is a different thing. And that's the inconvenient situation, inconvenient matter here. These two phrases sound very similar, but they are sort of like, in a sense, separated from each other. So let x, y be metric spaces. As usual, if you want, you can think of x and y to be subsets of the reals. It doesn't really matter. And I'm going to take f to be a function from x to y. Then I haven't even told you what uniform continuity is, but first I'm going to say, well, it's something that is stronger than continuity. Meaning, the first part is going to be, if f is uniformly continuous, then it is continuous. And second part, you can turn this around, assuming x is compact. If x is compact, any sequence in x has some subsequence that converges to some point in x. And f is continuous, then it is uniformly continuous. In particular, any function taking real values defined on a closed and bounded interval is continuous if and only if uniformly continuous. Okay? So for the nice setting that we're focusing on, uniform continuity is the same thing as continuity. And that's why I'm not going to spend that much time on this. Just complicates terminology and so on. I may spend more time later. So in particular, if I is, well, if x, okay, I'll write it like this. If I is a closed and bounded interval, same thing as compact interval, remember, is a closed and bounded interval, then any real valued function defined on I is continuous if and only if uniformly continuous. defined on I is C0 if and only if uniformly continuous. I'm not going to introduce a notation for uniform continuity. I'm introducing notation only for things that should be fast for you to think about. Okay? So for the good case for continuity, for the prime case that we're interested in, uniform continuity is the same thing as continuity. Okay? You can just take it as that. The definition of it, and that's why I've postponed it, is this. It's a bunch of epsilons and deltas. The idea is that instead of the delta depending on the base point you're looking at continuity, you get to choose for any epsilon some delta that works for any base point. Okay? So I'll write the definition here. I'll write it here. I'll put an example here. Okay, I'm not going to put the example here also. Metric spaces and f be a function from x to y. Instead of first fixing an x star in x, I'm just going to go ahead and define uniform continuity. It is not based on at a single point. Then f is uniformly continuous if for any epsilon, there is a delta such that for any x1 and x2 in x, if the distance between x1 and x2 is at most delta, then the distance between f of x1 and f of x2 is at most epsilon. Looks very similar to the definition of continuity. In the case that we're interested in, it is the same thing as continuity in the case of closed and bounded intervals. But it's more stronger in general. And the way I think about it is, you see, this is sort of like a relative thing. If this one of these x's were all the way here, that would be the definition of continuity. But instead of first fixing an x and then thinking about f is continuous at this point, you choose your epsilon and delta, and then x1s and x2s come. And that makes all the difference somehow. The example, the standard example, and I think this is the one in the textbook also, is 1 over x, 0, open. I might spend a couple more minutes about this. So let's say I is 0, 1, 0 not included. F is defined on I, taking x to 1 over x. Okay, so this is a function that is continuous but is not uniformly continuous. That's fine. That's not a contradiction to the theorem, but because this is not closed and bounded. Okay, not closed. Okay, continuity is different than uniform continuity. This is continuous but not uniformly so. Okay, I'm out of time. We're going to stop here. Tomorrow we're going to continue talking about this a little bit more. Thank you. All right, let's start. Good morning. So I'm going to take attendance today. So I want to say a couple more words about this uniform continuity. Like I said yesterday, for functions defined on closed and bounded intervals taking real values, uniform continuity turns out to be equivalent to continuity. That's why I'm bypassing it for now. In general, they're not exactly the same thing. We're going to talk about an example, and then we're going to transition to different notions of convergence for sequences of functions. And once we're done with all this, probably we're not going to do this today, but we're going to really start calculus proper with integral calculus, the first part. OK, so I just wrote down the definitions of continuity and uniform continuity using logical symbols. So if I take a function f from x to y, x and y are here arbitrary metric spaces, but if you want, you can think of them as subsets of reals. This function f is continuous if it is continuous at any point, x star. Well, for any x star, for any epsilon, there's a delta such that for any x, if the distance between x and x star is bounded by delta, that implies that the distance between their images is bounded by epsilon. That's the definition of continuity. One thing you can say here is, really, this delta, in principle, is a function of both epsilon and the x star. So sometimes you would see delta of x star epsilon. OK? The definition of uniform continuity is, it looks very, very similar. The only difference is that instead of having here one choice of a point in x and another one at the end, well, you start with the epsilon, then you have the delta, and then you fix your 2 points at the end. So from a logical standpoint, these two look very similar. Okay? So the only difference is, instead of having this here, you put it in the end. So instead of choosing one x in the beginning and one x in the end, you choose both x's in the end. The point here is that in this expression, delta is, so to speak, constant in x1 or x2. It's a function only of epsilon. OK? You might see this notation. And that sort of like also gives you a hint as to why this is called uniform continuity. Uniform in the sense that for any epsilon, there's a delta, choice of delta, that works uniformly for any x. That's why it's called uniform. What we're really going to be focused on is something else, which is this uniform convergence, but it's not really related to this uniform. Okay? It's a different type of uniform, and that's why I'm sort of not spending that much time on this. I think it makes things confusing. Just to give you an example, though, like I said, on a closed and bounded interval, these two are the same, but if you don't have a closed and bounded interval, things might be different. So for instance, if I were to think of I, 0, 1, 0 not included, 1 included, and if I were to take f to be the function that goes from I to reals, well, it's just a 1 over x function. Okay? I can immediately say that this is a continuous function because it's the ratio of two continuous functions, 1 and x. You can do it that way. There was an exercise I had given you. That's my exercise. This is sort of the fast way of doing this. The more explicit way of doing this would be something like this. Well, you would take an x and a nearby point, so to speak, x plus h. X is a positive or h is a positive or negative number, so that both x and x plus h are in this interval. Well, I just open up the definition. F of x plus h, when I plug it in, is 1 over x plus h. F of x is 1 over x, and I'm just looking at the distance between these two. So I'm taking their difference, and then I'm taking the absolute value of that. So I'm taking the absolute value of this expression, and then when you sort of rearrange everything, you have an h in absolute value in the numerator and x times x plus h in the denominator. Okay? Now, in this expression, if x is fixed, as h goes to 0, what is the limit? 0. Right? So numerator goes to 0, denominator goes to x squared, limit is 0. At this point, I think it's safe to just transition back to our Calc 1 understanding of functions and so on. So as h goes to 0, this goes to 0. And this represents the fact that for any fixed x, f is continuous at that x. So this is continuity. At any point, f is continuous. However, if I were to take x to 0, so now I'm moving my base point, what is the limit of the same expression? Infinity. Now there's a blow up, okay? So as x goes to 0, which means on this interval I'm going to the left all the time, this expression blows up. The fact that this expression blows up as x goes to 0 means, when you sort of unpack everything, that this function, even though it is continuous, it is not uniformly continuous. Okay? That's a distinction. And this much is enough. All you need to know, at least for now, is that if you have a possibly non-bounded or unbounded or possibly not closed interval, when you're working with continuous functions, remember you have to be careful. And in particular, uniform continuity may not be the same thing as regular continuity. Does that kind of make sense? OK. So here's a nice exercise. We're done with uniform continuity. In the textbook, there are more details and so on. I'm not going to spend that much time on these. We have more important things to discuss. So here's the exercise. I take two metric spaces, x and y. And as usual, I can think of these, if you want, as subsets of the reals. Then I have the set of all functions from x to y. Because after all, metric spaces are sets. So I can think of all functions between them. On the set itself, I want to define a metric so that I can talk about distance between two functions. Okay? And so this I'm going to denote by d sub c0, d sub c0. And it's going to take this d function itself is going to take two functions, both from x to y, and it's going to send it to this expression. First, you take an arbitrary point x in x. You feed the same point both to f and g. Okay? Now these are points in y, which means that I can look at their distance with respect to the metric of the y metric space, which then gives me a number. And then I'm going to take the sup of all of these expressions. It turns out, and this is the exercise, this function satisfies the three axioms that defines a metric, namely triangular inequality, symmetry, and point separation, or function separation in this case, if you want. Okay? I'm going to leave this to you. This is a very nice exercise in the basic properties of the supremum and essentially the absolute value function. If you want to sort of verify these in the context of x, y being subsets of the reals, then instead of this, you would just have f of x minus g of x in absolute value, and then you would take the sup of that. Okay? The only problem is that this is not quite a metric, because in principle, this function can take the value infinity. Some people would call this an infinity metric. It's not technically a metric, so somehow we need to do something about prohibiting the sup actually becoming infinity. What you can do is, instead of looking at all functions, you can just look at bounded functions. In this more general setting, a function is bounded if the diameter of its image is finite. Diameter is a notion that you're going to encounter in problem set 4. The idea of the diameter is rather nice. you take any 2 points, and you look at the distance between these two, and then you take the sup of all such distances. So that if you had a ball like this, the diameter indeed would be the diameter that you know. So this diameter, diam of a subset A, is d of xy, where xy in A, then you take the sup of these. You take all possible pairs of points, you compare their distances, and then you look at the sup of all such distances between pairs of points sampled from your subset A. In any event, this matches with the definition of boundedness in case y is equal to r. And on this set, this d sub c0 defines a true metric in the sense that it is a finite number always, although it could be unbounded in principle. And likewise, I can look at the continuous and bounded functions. On that set too, it's a metric. So these are going to be our important function spaces. First examples of function spaces. And the definition is, well, this metric for functions is called the supremum metric, or C0 metric, or L infinity metric, uniform metric. It has billions of names. I'm typically going to call it C0 metric. The C0, L infinity, or maybe uppercase L infinity. Uniform, or supremum metric. Okay, DC0 in the exercise. I'll transition to examples in a second, but this is the general definition. Any comments or questions about this so far? Yes?
Is that symbol L?
Yes. Capital L infinity. Those of you who are going to take more advanced analysis classes, you're going to learn what this means later. We're not going to need it. We're just going to call it C0. Because really, from my perspective, why are we using C0? Let's remember, because C0 functions, continuous functions, are those functions that you can approximate up to order 0. And I want to call this the C0 function, C0 metric, because somehow this tells me the distance between two functions, but it doesn't incorporate anything about higher order derivatives. It only tells me distances between positions. Later on, we're going to look at C1 metric, C2 metric, and so on. For now, we have only C0 metric. Okay. Comments, questions about this? So now that I defined a metric, then the natural way in which a sequence of functions ought to converge, well, it should be with respect to this metric. Okay? When that happens, that is called uniform convergence. Let x, y be two metric spaces, and let me let f bullet be a sequence in this. I can take it here, actually. It doesn't really matter that much. I'm taking a sequence of functions this time. In a second, I'm going to give examples. Let me just define things. Let's say it starts from 0. I have a sequence of functions. Be a sequence of functions from x to y and let me let one f infinity to be one function. Then f bullet converges to f infinity. When I say this, that also corresponds to uniform convergence, if I want to emphasize, if the metric space definition holds. Then f bullet converges uniformly to f infinity if f bullet converges to f infinity with respect to the C0 metric. To d sub C0. I want to open this up. Let's continue here. F bullet converges to f infinity uniformly if and only if, well, limit as n goes to infinity of the distance between the nth term and f infinity is 0. That's what it means for a sequence of things to converge to something with respect to a specific metric. What does that mean? Let's write it in the case of x, y subsets of the reals. Opening it up. So this is equivalent. Okay, so you see, even though these are functions and so on, once you apply the d function, now this is a sequence of numbers. And I know what it means for a sequence of numbers to converge to 0. So that's what I'm going to open up first. So for any epsilon, there is a capital N such that for any lowercase n after capital N, I want to say that this guy is bounded by epsilon, but then I can open this up because it is a sup, and I can say for any x in x, the distance between f sub n of x minus, or distance between f sub n of x and f sub infinity of x is bounded by epsilon. This is what it turns into when you open it up. That is uniform convergence. I'm going to define pointwise convergence now. Pointwise convergence is going to be something, in general, much weaker than uniform convergence. And then I'll start talking about examples for the rest of the class today. Let xy be two metric spaces f bullet be a sequence of functions and f infinity be one function. I'm going to say f bullet converges to f infinity pointwise. Okay? converges pointwise to f infinity if, okay, instead of using the C0 metric, what I'm going to say is, well, for each x in x, well, if I were to feed x to this sequence, I would get a sequence in y. And if I were to feed x to this, I would get a point in y. I want that sequence in y to converge to the corresponding limits. So if for any x in x, f bullet of x converges to f sub infinity of x in y. Again, let's expand what this means. And so f bullet converges to f infinity pointwise if and only if, you see this time I'm not using the C0 metric, but I'm going to use the metric on y. For any x in x, limit as n goes to infinity of the distance between f sub n of x and f sub infinity of x is 0. And again, let's open this up in the case of x, y being subsets of the reals. Orders of the quantifiers matter. Okay, for any x in x, I want to say that this sequence of numbers goes to 0. Now I need to do this epsilon delta stuff or epsilon n stuff. Now it turns into this. Looks very similar, at least from a logical point of view, but I've introduced lots of sort of extra structure, this C0 metric and so on, so that you can sort of distinguish. As you see, from a logical point of view, these look very similar. And in fact, the only difference, again, is when you choose this x. If you choose it before epsilons and n's and all that stuff, that is pointwise, that is the worst kind. If you choose your x at the end, that is the better kind. And in fact, I'm going to leave that to you as an exercise to show that uniform convergence implies pointwise convergence. Just to reiterate, here x is here, here x is there. If you want, this capital N is a function of both x and epsilon. On the other hand, this n is not a function of x, or it's a constant function of x. Okay. If a sequence of functions converges uniformly to f infinity, then it also converges pointwise. Okay? But we're going to see not vice versa, even in the best cases. And the rest of today, we're going to look into examples. Exercise: uniform convergence implies pointwise convergence. Any comments or questions so far? Okay. Now, when you try to sort of understand such matters, you should focus on sort of functions that you're familiar with, typically like polynomials and so on, trig functions, exponentials, these kind of matters. But in a sense, at least I find it somewhat hard to visualize functions whose graphs are not sort of piecewise linear. So I would suggest trying to use functions whose graphs are made up of finitely many line segments. These are what are called piecewise linear. And I'll say it like this. OK, I'm not going to define it, but these are the types of functions I'm going to look into. Let's first look into this. Let's say, let's start with this. I'm going to look into a sequence of functions. Let's say, starting from 1. And in fact, these are going to be all continuous, defined on the closed and bounded interval I, 0, 1. Okay. Now, I want to think of each function in terms of its graph so that I can visualize what is happening. And even before worrying about the formulas that define f, I'm going to try to come up with the visualization with the image. OK. So I want to think of it like this. I have this 1/2, 1/2 point. I want to think of that as a hinge, OK? And I'm going to start with a sequence of functions such that the graph of each of these is one line segment, such that as n goes to infinity, these guys sort of turn into this. Here's what I mean. My f1 is going to be the constant function, which is exactly 1/2. Let's not worry about the numbers for now. OK, it's a constant function like this. This is 1/2. This is 1/2. OK. Then for f2, I'm going to take this, and I'm going to rotate the shape just a little bit. OK. Something like this. OK. For f3, I'm going to keep rotating this a little bit more, maybe like this. That's f3. Do we kind of understand what the sequence of functions is in this case? No? So each of these terms is one term in my sequence of functions. F sub 1 is the function that is constantly 1/2. That's certainly a continuous function. OK? Now, f sub 2 is going to be, again, a function whose graph is this line segment. But it's that line segment is going to be tilted just a little bit more. To be a little bit more quantitative, perhaps you can put numbers here. I want this ultimately go to 0, to go to 0. So this is 1/2 plus 1 over, let's say, 3. OK? This is, oh, it should be minus, of course. Minus, I'll draw it bigger. going to be something like this. And this is going to be 1/2 minus 1 over, let's say, 3. And this height is going to be 1/2 plus 1 over 3. Okay? Does that kind of make sense? That's the second function in my sequence. Then for the third function, I say, OK, so let's let f3 have a line segment as its graph that goes from 1/2 minus 1 over 4 all the way up to 1/2 plus 1 over 4. I don't want to do that. I'll do it like this. 1 minus. OK. So say it's like this. That's going to be f sub 3. On this side, it's going to be at 1 over 2 minus 1 over 4. And on this side, it's going to be at 1 minus 1 over 4. OK? So what is the general formula then? Just draw the nth one. F sub n, okay, is going to be the function whose graph is this line segment, where on this side it's at height 1 over 2 minus 1 over n plus 1. Okay, and on this side it's at 1 minus 1 over n plus 1. Make sense? That's a sequence. For each n, I have a different function. Can you sort of animate this picture in your mind? So in the sequence, at time 1, I'm here, and at time 2, I'm here, time 3 like this, and eventually this sort of goes to the diagonal. Okay. You see, one can write down the definition, or rather the formula, explicit formula for f sub n. But when you're trying to visualize things, or when you're trying to come up with an argument, it's easier, as far as I'm concerned, to first try to come up with the shape of something, and then, if needed, you can come up with the formula. And in this case, for instance, I can do something like this. I know the equation for a line that passes through 2 points. So I know that this function is going to be a line in general, and it passes through 0, 1/2 minus n plus 1, and at 1, it passes through 1 minus 1 over n plus 1. Okay? So what I can do is I can do something like this. Plug these into these to solve for m and b. This is a unique solution, so that would give me the formula for f sub n. Okay, so m sub n, if you want, and b sub n would give me this. I'm not going to write this down, but I'm not going to compute this, but this is essentially how you would do this. Okay, this is standard Calc 1 stuff. This is my sequence of functions. Okay, that's an example. Each of these is continuous. And I want to call f sub infinity to be the diagonal function, y equals x. Okay, like this. Now, my claim is that the sequence of functions converges uniformly to f sub infinity. It's kind of clear from the picture also. Okay. As I take n to infinity, this sequence of functions, well, as n goes to infinity, this is going to be tilted more and more towards the diagonal. So this is going to go up, this is going to go down. I want to say that in the limit, in the uniform limit, you have f infinity. So that's the claim. Now, when you open this up, you get this. Right? So I can get rid of this absolute value and sort of distribute it and so on. That would tell me for any x in x, in this case I, f sub n of x is upper bounded by f sub infinity of x plus epsilon and lower bounded by f sub infinity minus epsilon. Now in that graph, these are heights, okay? What that corresponds to visually is this. You look at the graph of your target function, and then you take an epsilon strip around it. Okay, so in a sense, you take this line and you thicken it by an epsilon. Say here's my epsilon, and here's my minus epsilon. Okay. Now I have this band of width 2 epsilon centered at the graph of f sub infinity. In order for f bullet to converge uniformly to f infinity, what has to happen is, after finite time, the graph of f sub n ought to be completely within this orange band. So graph of f sub n is completely within this, let's call it b sub epsilon, epsilon band, for all but finitely many n. Okay? That's uniform convergence. In this case, of course, I hope you would agree with me, insofar as this 1 over n minus 1 over n plus 1 is less than epsilon, that is going to happen. Or maybe I need both this and this. Continue here. So for the graph of f sub n to be within b sub epsilon, what do I need? I need that this endpoint is within an epsilon. 1 over 2 minus 1 over n plus 1 is at most epsilon. And then this separation, so that is 1 over n plus 1, that is also less than epsilon. Okay, so given epsilon, you want to solve this for n. Oh, of course, this is a solution by the Archimedean principle, right? So there's not much to do. So given epsilon by AP, there's an n that satisfies these both. So that gives you a proof for uniform convergence. In this case, the functions are rather explicit, so you can actually come up with an explicit function for n, exactly when this is going to start happening. But we can just bypass that by just referring to the Archimedean principle. Okay. This is uniform convergence. Any comments or questions about this? This is really one of the hard parts of this course. Here's another example. Okay. This time you're going to see it's not going to be uniformly convergent, the sequence that I'm going to draw. Again, I'm going to look at a sequence of functions defined on the closed and bounded interval 0, 1. And they're going to be piecewise linear, meaning their graphs are going to be made up of finitely many line segments. And I is 0, 1. Defined like so. This time, instead of using this tilt motion, I'm going to use something like a wave. I'm going to start with a wave, and I'm going to sort of keep pushing it in one direction. Okay. Let's divide it by 2, and then like this, and so on. So I'm dividing this at, so this length is 1/2, this is 1/4, this is 1/8, and so on. Okay. F sub 1 is going to be this triangular wave. Okay. That's f sub 1. That's a function, and it's a continuous function. Again, if you want, you can draw you can write down the formula for it, but it's not going to help that much. F sub 2 is going to be a similar wave, but I'm going to push it, and I'm going to use only the smaller part. Okay? So it's going to look like this. That's f sub 2. Okay. So this time I'm pushing my functions this way. F sub 3, again, is going to be a wave of same height, same amplitude, but it's going to be supported on this even smaller interval. Like so. That's f sub 3. So if I wanted to come up with the general formula, I would look into this. Oh, not this one. So I'm going to look at one of these smaller intervals, maybe like this. And what are the endpoints going to be? Well, they're going to be of the form 1/2 to the n, and then 1 over 2 to the n plus 1. There are other things you can use, but that's what I thought of doing. It should be the other way around. I'll do it with the 1 minus, actually. 1 minus 1 over 2 to the n, 1 minus 1 over 2 to the n plus 1. Okay. Okay. So this interval, as n goes to infinity, sort of accumulates to this, to 1. So for instance, here this is 1 over 2, 1 over 1 minus 1 over 2, 1 minus 1 over 4, 1 minus 1 over 8, and so on. So at 1, my subscript is 2 to the 1. So that should give me the graph of the nth function. Okay. That's my sequence of functions this time. Okay. Again, let's try to animate this in our heads. You start with like a large triangle here, and as time goes by, this triangle gets squished, and at the same time it's approaching to this, approaching to horizontal 1. Okay, that's what is happening with this sequence of functions. Any comments or questions about this example? Now, here's the bizarre thing. If I were to compare any two functions in this sequence, in fact, their distance with respect to the C0 metric is 1. For any n and for any p positive, I'm taking two distinct terms. Okay? What is the C0 distance between these two? Sup of f sub n of x minus f sub n plus p of x in absolute value, where x varies between 0 and 1. But here's the thing, you see. Because I chose p to be positive, the picture is going to be something like this. This is where f sub n sort of has this spike, and somewhere else has f sub n plus p, the spike. So if I were to take as my x value something here, well, f sub n of x is going to be positive, and at most it's going to be 1. On the other hand, f sub n plus p of x is going to be 0. But since I'm going to optimize over all x's, this is always going to be 1 for me. So with respect to the C0 metric, even though it looks like these guys might be converging to something, and they indeed converge pointwise, which I'm going to discuss in a second, they cannot be converging uniformly. Because for a sequence of things to converge uniformly, eventually this has to stabilize. Okay. Cannot converge uniformly. Somehow in the space of continuous functions, any two such functions are 1 distant apart from each other. So they don't get close to anything. It's very bizarre. Oh, I'm out of time. We're going to continue tomorrow. Thank you. All right, let's start. Good morning. So today I want to finish up the discussion regarding this uniform convergence of functions. We had discussed two examples. well, we started talking about the second example. I want to finish that. I want to give yet another example, give one statement about why uniform convergence is rather nice. And then we're going to transition to what I would think of as integral calculus proper. Namely, we're going to start with integral calculus. First, in this first example I gave, one of your colleagues at the end of class mentioned that these numbers were wrong. So this is the corrected version. Instead of saying 1 over 2 minus 1 over n, I should just be taking 1 over n on this side. So that as n goes to infinity, this side goes to 0. And in this case, I've actually sat down and wrote the explicit formula for f sub n. So and I'm changing the index just a little bit so that things are slightly more convenient. Typically, I find it more convenient to use for f sub n sort of the index inside the function as n as well. I don't like shifting this n around that much, generally speaking. I'd rather start my sequence at a different integer than sort of add +1 or -1, whatever, inside the function. But that's sort of like a matter of choice. And so when you open up the definition of the function, the formula for the function that passes through 2 points, we know from standard calculus that given any 2 points in the plane, there's exactly one line passing through them. And so this uniquely defines, in fact, the function. But if you want to be more explicit regarding your proofs, and in principle, you should be able to do this. Well, the limit, the target limit is x sent to x. It's a diagonal function. And so I'm trying to bound this, OK? And so when I plug in these expressions, all this does is it gets rid of this 1, and you have this, and then you rearrange things. And ultimately, you use the fact that x is between 0 and 1, in this case, that this distance is uniformly bounded by 3 over n for any x. Meaning, if I were to take an epsilon, I would be able to choose capital N large enough such that no matter what x is, this distance is bounded by epsilon. That's why f bullet in this case converges uniformly to f infinity. And I had given this as an exercise. It's a nice exercise. If you have a sequence of functions that converges uniformly, then that sequence also converges pointwise to that limit. OK? So the idea is what I discussed, but this is sort of more explicit, and the bounds are accurate this time. Yeah?
So what confuses me most is that you are comparing 2 functions.
Yes.
And one of the functions, the one you wrote in black, actually is just a very ordinary function. You designate it as f sub infinity.
Yes.
That's the confusion.
Well, you don't need to write that as f sub infinity. You can just use f if you want. I like using this infinity as a subscript to remind myself, oh, this is going to be my target point in the space of functions.
So you're comparing 2 functions.
Well, I'm comparing one function coming from the sequence of functions. For each n, I have a different function.
But for f infinity, no.
F infinity is one function.
Is a function that doesn't move with n.
No, exactly. This doesn't move in n. So this is stationary. It doesn't move in time. I'm saying when I put a subscript infinity here, I'm kind of saying this is the sort of the function that remains at the end of time. And everything is, when the dust settles, this is what you're left with. That's what that's my psychology in a sense. On the other hand, this is a function of n also in a sense. So this changes in time. Okay, so this is stationary, this is dynamical. Okay. Any other comments or questions about this? Now, on to this. Again, this time I'm not going to write down the formula. Again, we have the closed and bounded interval. And now, this time I have these triangular wave functions. Namely, at time n, this f sub n is going to have this tent sandwiched between 1 minus 1 over n, 2 to the n, and 1 minus 1 over 2 to the n plus 1. So as n goes to infinity, you see, each of these f sub n's are going to have the same general shape. But as time goes to infinity, this tent is going to get squished to this side. The claim was, well, in this case, this sequence of functions converges pointwise to f infinity being the function that is constantly 0 in this case. However, it doesn't converge uniformly. For uniform convergence, remember, what needs to happen is, well, this sequence of functions has to converge with respect to this C0 metric. If I were to take an arbitrary n and look at this distance between them, by definition, this is the sup of their distances compared at the same x value. So to compare the C0 distance between two functions, to figure out what the C0 distance between two functions is, what you need to do is you take any arbitrary horizontal and you compare the heights of the two given functions. Okay? You compare heights, you sort of scan this way, compare heights, and then you take the sup of all such height differences. So for instance, you see, so if x is somewhere here, both f sub n and f sub infinity are 0. But then as I move into this middle part, where I have the tent for f sub n, somewhere in between, in fact, what happens is f sub n of x is 1. On the other hand, f sub infinity is 0. Meaning, as I scan, okay, horizontally like this, okay, here, the distance between the height given by f sub n and the height given by f sub infinity is maximized, and that is indeed 1. So that means that within this space, metric space of functions, in fact, this tent shape and the flat line that is constant to 0 are always one distant from each other. Consequently, well, as n goes to infinity, it doesn't matter because these distances are always going to be 1, which means that they cannot be converging. Okay? So f bullet does not converge to f infinity. Uniformly. If there was uniform convergence, pointwise convergence would be automatic, but it might happen that you have a sequence of functions that fails to converge in this stronger sense, that fails to converge uniformly, but still converges pointwise. And this is an example of that. Okay, so for instance, I'm going to continue here. Claim f bullet converges pointwise to f infinity. Okay, so this is a weaker sense of convergence. So it might fail for your sequence of functions to converge in the strong sense, but just because it doesn't converge in the strong sense, it doesn't mean that it's not going to converge in the weaker sense. Okay? So what is the difference now? With pointwise convergence, you're going to fix a horizontal. You're going to fix an x value. You're not going to look at the sup, but you want for each x, this expression to go to 0. So i.e., for each x between in I, well, limit as n goes to infinity of the distance between f sub n of x minus f sub infinity of x is 0. Okay? So for uniform convergence, you see, instead of taking this x before the limit, we take it after the limit. And that makes it more strong. And so here's how we can prove this, for instance. We want to split, I thought of splitting into two cases. Either x is 1 or it is less than 1. If x is 1, then for any n, f sub n of x is 0, and so is f sub infinity of x. So for any n, f sub n of 1 is 0, f sub infinity of 1 is also 0, meaning their difference is 0. So the thing that you're taking the limit of is already 0, so it has to be 0. In this case, there's nothing to do. On the other hand, if x is some number less than 1, well, I'll draw here a picture. Say it's here, then. Well, the point is, as n goes to infinity, I have this tent, okay? And this tent sort of moves from this side to this side. Meaning in finite time, once I fix my horizontal, it's going to be somewhere here, but eventually it's going to be to the right of this x value. And once I pass this x value, well, as I keep n to infinity, all these tens are going to stay to the right even still. Okay? Meaning, in this case, there is a capital N such that for any lowercase n after capital N, this happens. 1 minus 1 over 2 to the n. Once you fix the x, as you take n to infinity, well, this expression, you know, converges to 1. So it's going to exceed x. But once this happens, by the definition of the function, that's going to mean, oh, OK, so x is somewhere here, but I took n large enough so that the tent is this way. But then if that is the case, it must be the case then that for this specific x, I have that f sub n of x is 0. So for any lowercase n after uppercase n, f sub n of x is 0, which is the same thing as f sub infinity of x. And again, there's nothing to do because they converge. So you have pointwise convergence. Okay. Just to reiterate the distinction between uniform convergence case, pointwise convergence case, well, here you see I could bound the distance between f sub n of x and f sub infinity of x by something that didn't depend on x. This means that for large enough n, the whole graph of f sub n is going to be within this 2 epsilon band around f sub infinity. On the other hand, here, even though I can, in fact, make this expression 0, that's going to be conditional when that happens. It's going to be conditional on x. In other words, if I were to take a small epsilon band around the target, well, you see, no matter what n is, there's going to be this spike that falls out of this small epsilon band around f sub infinity. And indeed, in this case, this capital N you can think of as a function of x. In this case, you can explicitly compute what the minimal capital N can be. I'll do it here. So I need this expression. Okay, I need this condition. Essentially, what I want to do is I want to come up with, I want to solve for n, this thing. Okay. So, for instance, I can do this. 1 minus x x is, in this case, less than 1, but it's also non-negative. In any event, this is a positive number, which means I can turn it into this. Take logs. You have this is upper bounded by n log 2. I don't really care what the base of this log is. Take the log 2 to the other side. You have this. Meaning, for fixed x, the smallest capital N that I get to use is, well, it's the ceiling of whatever this number is. So ceiling of this. This is, given x, the least amount of time you're going to have to wait to see convergence, to control what you're trying to control within an epsilon. Okay. Do you see this capital N in the definition depends on x. Depending on the base point x, well, I mean, I hope you agree with me. If x were somewhere here, I don't need to wait too long. But if x were near 1, well, then I would need to wait possibly a long time to guarantee convergence, to guarantee that the two things are close to each other. Okay? Because the idea is, once I fix my horizontal, I need to wait so that this 10th wave passes that horizontal. Make sense? Okay. Any comments or questions about this? Okay. I think I'll erase this. These calculations, these are not very important. I'll put here another example, but before that, I'm going to write down the statement. Here's the important statement. So these two senses of convergence for sequences of functions are distinct. That's what we saw. The benefit or the trade-off is this, okay? Pointwise convergence typically is easier to establish, easier to argue about, and so on. Uniform convergence, you see, it's already a more complicated expression. But there's a reason why you may want to consider this more complicated notion of convergence. And it is this, that if you have a sequence of functions that has a certain property, well, you would want the limit function, insofar as it exists in some sense, to have the same property also. For now, for instance, we would like to be able to say something like, if my sequence of functions is continuous and they converge, then the limit function is also continuous. It turns out that with pointwise convergence, this is broken, and that's going to be the example that I'm going to give in a second. But if your sequence of functions converges uniformly, then it is guaranteed that the limit function too is continuous. Let x, y be metric spaces f bullet be a sequence of functions and f infinity be one function. In fact, I'll write this like so. If for each n, f sub n is continuous, and f bullet converges uniformly to f sub infinity, then f sub infinity is also continuous. So the continuity of the limit function is automatic, insofar as you have uniform continuity. Before going into the proof, here's the example that you should keep in mind. Again, I is my closed and bounded interval from 0 to 1. I'm just going to think about the monomials x to the n. C0 like this, time n, send it to that function that takes an x and sends it to x to the n. Okay, so f sub n of x is x to the n. When you draw this turns into this picture. So this is f sub 1. It's a diagonal function, like so. 1, 1. F sub 2 is, well, it's the x squared function. So it is sort of caved a little bit like so. F sub 3 caves even further. Okay, that's my sequence of functions. And when you animate this in your head, it's like you start with this diagram, this diagonal, and sort of as time goes by, this sort of like gets bulbous this way. And somehow, as n goes to infinity, you should basically get this side of the square, which is essentially what happens, but certainly that's not a function necessarily. But it turns out that f sub infinity defined by x sent to 0 if x is less than 1 and 1 if x is 1 is the pointwise limit of f bullet. So this is this following discontinuous function. F sub infinity is not a continuous function. Okay? Purely by the fact that f bullet is a sequence of continuous functions, you can, once you verify that they converge pointwise to f sub infinity, you can conclude that this cannot be a uniform limit by the theorem. Because if it were, this would have to be continuous. Okay? So f bullet converges to f infinity pointwise, but not uniformly. And just to reiterate, this example is when f bullet converges to f infinity pointwise, but not uniformly also. So if you have a sequence of continuous functions that converges pointwise to some other function, well, essentially you're on your own regarding the continuity of the limit function. It might happen that the pointwise limit is continuous, as in this case, or it might happen that the pointwise limit is discontinuous, as in this case. Okay, the theorem doesn't say anything about that case. It says if you have uniform continuity. And in fact, I'll leave it to you as an exercise. You can sort of change this property to other things. For instance, if each term in your sequence is uniformly continuous, then the limit function is also uniformly continuous, assuming uniform convergence. Or if each of these functions are bounded, is bounded, then the limit is also bounded. So exercise. Can replace C0 with uniformly continuous or f sub b, bounded function. OK. So we need to prove this. I'm going to leave the general metric space case to you. The argument is verbatim the same, but I'm going to assume x and y are subsets of the reals and use this absolute values and so on. So I'll put it as an exercise also here. General case of the theorem. I'm going to prove the theorem assuming x and y are subsets of the reals. Okay, so I have these two, and I want to show that f sub infinity is a given function. It's the uniform limits of a sequence of continuous functions. I want to show that this limit too is continuous. Well, we can do it like this. Let x star be in x. I want to show that this function, f sub infinity, is continuous at x star. If you want, you can use sequences as well. In this case, sequences of numbers or sequences of points in x. But let's try to use this epsilon delta stuff. Instead of choosing epsilon, again, I'm going to try to start from the end of the proof. Meaning, I'm going to start with the expression I'm trying to control. Then, for any x in x, I'm going to add one more thing here probably, but let's keep going. I start at the end, OK? Ultimately, I'm going to try to control this. I'm going to try to say something like, if x is close enough to x star, this expression is close to 0. So I start at the end. I told you that pretty much the only thing that you use in these type of situations is a triangular inequality. So I'm going to inject a bunch of terms so that I have a bound for this in terms of things I can already control. So what I can do is this. F sub n and this for any n. I injected, subtracted and added f sub n of x into this, and then split, and then I subtracted and added f sub n of x star. And again, use triangular inequality. OK? Well, for any x, this expression is upper bounded by the C0 distance between f sub n and f sub infinity. And so is this. So this is upper bounded by twice the C0 distance between f sub n and f sub infinity, plus this expression. At this point, I think it's OK to stop using epsilons and stuff explicitly if you want. We can at this point say, as n goes to infinity, this goes to 0 by uniform continuity assumption, and this goes to 0 also by the assumption that f sub n is C0. Okay. As n goes to infinity, this goes to 0. as x goes to x star for fixed n. Meaning I was able to bound what I'm trying to bound in terms of things that goes to 0, which means that ultimately the limit has to be 0. That's a proof. Okay. You can be more explicit about these kind of things if you want, but I think you've had enough experience, and if it is somewhat confusing, it might be good to think about it, but I think these kind of things are, admissible at this stage. Perhaps the one thing that should be that you should be careful about in this kind of matters is that so this is easy to control, but this is slightly more dubious to control. Okay, because somehow for each n, f sub n is continuous, but in a sense, in the epsilon delta definition, then for any epsilon, the delta that you're going to use in this case is going to depend on n as well. So if you want to be more proper, what you would say is something like this. You would say, OK, I'm trying to bound this by, let's say, some epsilon. To bound this whole thing by epsilon, what I can do is I can try bounding this by epsilon over 2 and this by epsilon over 2. To bound this by epsilon over 2, I need to bound this by epsilon over 4. I know that f bullet converges to f infinity uniformly, which means that there is some capital N such that this distance is bounded by epsilon over 4. For that capital N, you would use the fact that f sub capital N is continuous to then get a bound for this. Okay. Maybe it's a good idea to write this down, actually. This is sort of like the fast way of doing this, but if you want to be more explicit, here is a more explicit way of doing this. So this is bounded by this, OK? I'm just going to take this expression. OK. Blue star. In fact, I'll just summarize it here again. What it says is this. For any x star and x in x, and for any n starting from 0, I have that f sub infinity of x minus f sub infinity of x star in absolute value is upper bounded by twice the c0 distance between f sub n and f sub infinity plus f sub n of x minus f sub n of x star. I just summarized this. If you want to be more proper, this is how you would conclude this proof. So let epsilon be positive by the assumption that f bullet converges to infinity uniformly. There is some capital N such that this is bounded by epsilon over 4. Since f bullet converges to f infinity uniformly, there is some capital N such that the c0 distance between the capital nth term and the infiniteth term is bounded by epsilon over 4. Since f sub capital N, this specific function, is continuous, there is a delta positive, such that for any x in x, if x and x star is at most delta apart, then this distance is bounded by epsilon over 2. Hence, given epsilon, there is a delta such that for any x in x, if x and x star are at most delta apart, by star, f sub infinity of x and f sub infinity of x star is, well, this is bounded by epsilon over 4, which means this is bounded by epsilon over 2. This 2 is bounded by epsilon over 2, which means that the whole thing is bounded by epsilon. That's how it ended up. Okay, so this is a more explicit way of doing what I did over there. Needless to say, often people just would leave it like this. And they would be careful about these dependencies and so on, because there's a bunch of like things that sort of move essentially independently of each other. And so you need to sort of like synchronize them to get really the bounds that you need. So if you're sort of getting confused, it's always good to go back to the epsilons and deltas and make things super explicit. But this is also perfectly valid for us. Okay. So what I wrote over there literally essentially means this underneath the hood. So I have this, I have that. Okay. Comments or questions about this? Okay. Question?
I actually have a question. So you've been talking about converging uniformly, converging pointwise, only in the context of sequence of functions?
Yes.
Is it exclusive to sequence of
Yes.
functions? Okay.
Yes.
Okay. And then if it converges pointwise, does that mean that the functions converge to a point but not to the same function? Is that
No.
a succinct way of
So when you're talking about a sequence of functions converging, the limit is always going to be, no matter what the sense of the limit is, it's always going to be a function. Okay? So pointwise versus uniform convergence is all about whether or not this distance, this expression over here, for instance, whether or not, oh, maybe not that expression, but this expression over here, I'll do this. You have a sequence of functions, and that is f sub n. Forget about everything. You have something like this. This is what you're trying to control, no matter what the sense of convergence is for sequences of functions. You have f bullets, f sub n. It's a sequence of functions that depend on time. And f sub infinity, a supposed target function. Well, how do you figure out their distance? You feed to them the same x value, and you're comparing the heights. Ultimately, when you're trying to show in whatever sense this convergence happens, okay, ultimately, eventually, it's going to turn into an expression like this. And you're going to want this to be approximately 0. Okay, for large n. for n large. Or n near infinity. Okay, so far? Now, the distinction between pointwise and uniform convergence is, well, it's about these approximations. If you can make this sense of nearness independent of the x value, that is uniform convergence. If, on the other hand, this approximation intrinsically depends on the x value, that is pointwise. Does that kind of make sense?
Yes, it does.
Yeah. It takes a while to get accustomed to this. But there's a reason why I define sequences of functions like this in a bizarre fashion. See, in the abstract setting, what is an independent variable and what is a dependent variable, these questions end up being rather confusing because these are not necessarily rigorous terms, really. It's not really clear what is an independent variable. So I told you when we first started talking about sequences at large, oh, that bullet, okay, that stands for the time. So in this sequence of functions, this is my notion of time. If you want, you can think of this as your space. So this is your space, this is your time. In time, something happens. Yeah. Any other comments or questions about this? We have like 7 minutes, which is good. I just want to start introducing some ideas regarding integral calculus. First, I want to say, why not first do differential calculus instead of integral calculus? Well, we could. That's the standard way of doing things. But in principle, there's nothing stopping us from doing that. Second of all, it turns out that the rigorous description of differential calculus is a lot more simple than the rigorous description of integral calculus. So this Riemann sums and stuff like that, they end up being rather complicated. So we're going to do the complicated thing first. And then we're going to take a break with differential calculus because the third part of the course, analytic functions, they're also complicated. So instead of starting easy and then having two topics that are complicated, namely integral calculus and real analytic functions, first we're going to do the more complicated thing, then take a break with differential calculus, then sort of amp it up again. Last time I taught this course, a lot of students sort of fell out during integral calculus because we were covering it toward the end of the course, namely 2 or 3 weeks later, and then other courses are getting more complicated at that stage also. Becomes harder, I think. Yeah, so what we're going to do is we're going to spend approximately 3 weeks following this Fonda book as well. It's in the Canvas, if you want, the first chapter, which is the chapter that we're going to use only. So we're going to mix and match. We're going to spend 3 weeks doing integral calculus. Then we're going to discuss differentiability from an abstract point of view. We're going to rigorously define things. Prove things like the mean value theorem and so on. Then I think we're going to discuss Taylor approximation. No, we're not. We're doing Taylor approximation after the fundamental theorem. Okay, so 3 weeks integral calculus, 1 week differential calculus, then 1 week on fundamental theorem of calculus, then Taylor, then real analytic functions. That's going to be our where we're going. So here's the general idea. From a modern perspective, Well, an integration theory turns out to have essentially two components. One of them is, well, you want what is called you want a collection of functions that you deem integrable. And, well, you would like to associate to each function that you deem integrable some number that is supposed to be the integral of that number, of that function. So integration theory a family, let's say, curly C of, in fact, let's write it like this. Say you have I, a closed and bounded interval to begin with, a family of functions on I taking real values, and a function, let's call it curly I, that goes from C into reals. Okay, C, then you say, is my space of integrable functions, and I of f for any f in C is the integral of f. So C is the collection of integrable functions, and for any f in C, you want I of f to be integral of f. Probably you want some properties regarding both of these. Probably you would like to be able to integrate at least continuous functions. Ideally, meaning the continuous functions are inside your collection. The integral of the sum of two functions, well, you should be able to split it. You should be able to scalar multiply. And you should have some sort of domination. If for any x in I, f of x is less than or equal to g of x, then the integral of f probably is, well, probably should be less than the integral of g. Okay. Now, probably in the next problem set, I'm going to give you one integration theory that is like very bare bones, that basically uses this, just like wants some axioms and defines an integration in terms of uniform convergence of a sequence of functions that are supposed to be obviously integrable. So this is what is called the regulated integral theory. Probably in the next problem set, I'm going to give that to you. It's very bare bones, even compared to Riemann integration. But given this, so this is essentially where we're going. It turns out that from the modern perspective, there are exactly two paradigms that turns out to be very useful. Okay, one of them is the Riemannian paradigm. The other one is the Lebesgue paradigm. I don't have time to go further into detail today. We're going to talk about this on Friday also. Thank you. All right, let's start. Good morning. So today I'm going to take attendance. Today we're going to start talking about calculus proper, starting with integral calculus. So we're going to postpone differential calculus for a while, develop integral calculus to some extent, then introduce to the mixed differential calculus, mix them up to get fundamental theorem of calculus, one version of it at least, or a couple versions. And then we're going to be on our way. So today it's going to be somewhat more broad in a sense. I want to give you a picture as to what integral calculus is about, broadly speaking. I'm going to give you some ideas. And if time permits, we're going to start with Riemann integrability as well. So the modern understanding of any integration theory is, well, it's a pair, C and I, where C is a class of real valued functions which you deem T integrable, so integrable with respect to your integration theory. And I is a function that goes from your collection of your class of functions to reals. That is to say, it associates to each function that you deem integrable some number called the integral of that function with respect to whatever theory you're looking at. In principle, using real valued functions are not necessary, but since this is a single variable class, that's what we're going to worry about mostly. And typically, you want some sort of properties for these pairs. Some of the algebraic properties you would want is certainly you would want this I to be additive, meaning you want the integral of the sum of two functions to be the sum of the integrals. You could perhaps also think of this as an intuitive property, but you would want the integral of some constant, so some scalar multiple of some function to be C times the integral. So you should be able to take the constants out. These are sort of some of the algebraic properties you may want. For intuitive properties, well, you would want certain types of functions to be in your class. Maybe constant functions, and somehow integral of f in sort of like a more standard setting should correspond to the area underneath the graph. So you probably want something like this. So if you have two functions like this, say, that is to say, the graph of g is always above the graph of f, then the integral of f should be dominated by the integral of g, so that you can kind of think of I of f as the area underneath, or the volume underneath the graph. And also probably, if you're taking a sequence of functions that converges to something, you would want the integrals to converge also. Meaning, limit as n goes to infinity of I of f sub n, probably you would want this to be the same as the integral of the limit. Okay. Of course, at this stage, we should be worried about what sort of a limit this should be. Is it pointwise? Is it uniform? Whatever. That does end up being a major issue. We're going to discuss that. And probably you also want this I function to work well with, so maybe I should say too. So this, C0 is included in your collection. So all continuous functions, all constant functions, maybe all sort of piecewise continuous functions. You would want all of these to be integrable. And we haven't developed differential calculus yet, but probably you want a fundamental theorem of calculus. Probably you want something like an integration by parts, things like this. So probably you want the integral of f prime to be f plus a constant, and you want the integral of f prime g to be integral of f g prime up to some constant also. Probably. Okay? You want such matters. So we're going to develop one, or maybe two, or maybe three sorts of integral theories that satisfy all of these in some senses, but it's going to take a while. Okay? Any questions about any of this so far? Now, yeah.
Just to clarify, we're creating the idea of an integral. This is what we want.
Yeah, probably these are the types of properties I would want. Exactly. So the meta idea, and those of you who are going to take more advanced classes is going to study this. It turns out that, in fact, pretty much any set is, or any class is a class of functions, and pretty much any function like this is an integral and vice versa. So this is what is called a representation theory or theorem. Typically, people would associate this to the mathematician Ries. Representation. So, meaning whenever you're trying to understand a class of functions with a specified scalar function defined on that class, that pretty much is an integration theory. You probably want things like this, but these are sort of like some reasonable choices. Okay. Now, generally speaking, there are two paradigms where you establish such an integration theory. For our purposes, initially speaking, the classes of functions are going to be functions, real valued, that are defined on a closed and bounded interval. That's what we're going to start with first. And then, if time permits, we're going to think a little bit more about what is happening, what happens if I try to integrate a function over an unbounded domain. Because certainly I would like to be able to make sense of expressions like this as well. Sine of x, e to the minus 5x dx. Turns out that this is a valid expression. And maybe some of you have seen this before. Have you seen things like this before? So this is really the Laplace transform of sine evaluated at 5. So turns out that in applications, this ends up being useful, being able to do these kind of things. But for now, we're not going to try to integrate functions over unbounded domains. We're going to focus on closed and bounded intervals. Remember, I told you when we were studying continuity that the sort of initial sort of habitat for continuous functions is closed and bounded intervals. And the same thing is true for integration as well, at least for us. So, two paradigms. One of them is what is called the Riemannian paradigm. And the other one is Lebesgue paradigm. Okay. So when I say paradigm, I don't mean a theory, because there is the theory of Riemann integration, meaning Riemann integrable functions together with Riemann integral. But it turns out, and this is the complicating part, you can interpret this Riemannian theory both from the perspective of the Riemannian paradigm and from the perspective of the Lebesgue paradigm. It turns out, again, this is confusing, there's a Lebesgue integration theory which you can interpret from this paradigm and this paradigm. Okay? So we'll talk about all this later. For now, I just want to give you a sense as to what the distinction between these two paradigms are. And I'm just going to draw pictures. I should mention, we're going to focus mostly on the Riemannian paradigm here, but the industry standard is Lebesgue paradigm, meaning those of you who are going to take more advanced analysis classes, graduate level, whatever, you're going to spend a lot of time developing this paradigm because it turns out that for things like Brownian motion, path integrals, a bunch of other things, somehow the Riemannian paradigm sort of starts breaking down rather easily. And That's why this Lebesgue paradigm is a lot more robust. So just to give you a sense as to the distinction, and for applications too, for most applications, this ends up being more useful. So the main distinction between these two is, well, ultimately, these are both eventually some sort of an intuitive integration theory. If I have, let's say, a continuous function defined on a closed and bounded interval, I want the integral to be the area underneath. In the Riemannian paradigm, the way you compute the area underneath is by chopping the domain into smaller pieces. So say f is continuous. Well, is continuous. To integrate it, chop 0, 1 into smaller pieces. Like I said, today is going to be not very heavy in terms of technicalities. So say I have a function like so. Okay, that's my function. Okay, this is my function. Integral of it should be the area of this shape. Okay? And so from the perspective of Riemann, what you do is this. You chop this into smaller pieces. And there's a couple different tricks that probably you've learned, but I'm just going to try to approximate the area from within. I'm going to try to exhaust this whole area using rectangles, essentially. So in the first step, I'm going to chop this 0, 1 into 2 equal pieces, like so. Okay? This is step 1. And then I look at it and I say, well, how can I exhaust this area using boxes that don't exceed this f? Well, there's nothing I can do here, so it's going to be just a constantly 0 function. But here, I can add this piece. Okay. So this doesn't contribute anything to my area, but this contributes 1/2 times whatever this length is. I'm saying my integral should be something intuitive. So ultimately, the integral of this smaller piece should be, well, the length of this times the length of this. That's step 1. Then you keep going. Okay? Instead of splitting only once, say you now split this piece into 2 smaller pieces and this too. Now this is step 2. Like this. And then I say to myself, given this finer partition, is what we're going to say, can I use more rectangles? Well, again, I can't quite increase this part, but here you see I have yet another rectangle that I can add. Something like this. And that's it. Makes sense? Because, see, I'm just trying to stay under the graph for now. By just partitioning the input space into finer pixels, I was able to make my approximation from within slightly better. Any questions as to what I'm doing here? So this was step 1. Step 2 was green. I'll do one more. Step 3 in blue. Now I chop each of these smaller pixels even further into 2 pieces. Now I'm going to use blue. Okay. Again, I can't add much here, but there's another rectangle I can add here, like so. Here there's a small piece I can add, like so. I can't add anything here. Here it seems like I can add just a little bit, almost negligible. I can't add anything here. I can't add anything here. I can add this small piece here. Make sense? Now you keep going. Okay? You keep partitioning further and further. And I hope you would agree with me that as I keep increasing my resolution, in other words, the size of my pixels, I'm going to have some sort of a diminishing return. Initially, I got this big chunk in red. And now I'm sort of like adding smaller and smaller pieces. Of course, the hope is, ultimately, as I keep doing this procedure, eventually this stabilizes, the total area stabilizes. And indeed, then I can call that limit the integral of f. OK? This is the Riemannian paradigm. Any questions about this so far? Now, there are certain complications here, which I'm going to discuss in a second. The main thing, of course, is that, well, at this point, you should be suspicious as to what sort of a limit is involved in this limiting procedure. Because probably you've seen, so for instance, here I've used endpoints of the form 1 over 2 to the n, but probably in Calc 1, you used 1 over n. OK, so that's a different partition, but ultimately it should converge as well. And so this is also like a lower approximation, but maybe, quite possibly, instead of using something like this, Riemann sums that you've seen before sampled certain heights from the function, maybe the left endpoints always, or the right endpoints, or the midpoints, and so on. So there are certain complications. And of course, it should be the case that in order for this function to be Riemann integrable, no matter how you do this procedure, the limit should always be the same. Now, of course, this is a complicated matter. And this is why integral calculus is rather hard to make rigorous. But underneath, what we're going to use is this limit of a net idea in problem set 4. So for each such partitioning, well, we have a proxy for the integral. And that's going to give us a net. And then we're going to talk about, oh, this net converges. That's why in problem set 4, you've encountered that idea. Well, we'll talk about all that later. Somehow, we'll be able to stay within the paradigm of Riemann integrals or Riemann integration. And depending on what type of a net you think of for these partitions, you end up getting different results. Sometimes you end up getting different results. Sometimes you end up getting the same results. But we're going to discuss all that. But this is essentially the idea. Any comments or questions about this? So now I'm going to switch over to the Lebesgue paradigm. We're not going to discuss this Lebesgue paradigm that much, even though, if time permits, we are going to talk about Lebesgue integrability, still though from the perspective of Riemannian paradigm. Okay? I'm just going to take the same function. To integrate, instead of this time chopping 0, 1, I'm going to chop the image. Okay? To integrate, chop image into smaller pieces. Again, I'm going to draw the graph. And try to draw the same function. Imagine this is the same function as that. Okay. Again, I have 3 steps. I'm gonna show you what happens in 3 steps. I guess I can make this a little bit more similar to the other one. Okay. Looks slightly better. So in step 1, instead of partitioning my domain, I'm going to partition the image. Okay? So I'm going to try to split it into two pieces, approximately of equal length. Well, this is slightly higher, but imagine this is at 1/2. And then I look at the sublevel sets, essentially. I look at the sublevel set of 1/2, and I get this. Okay. Again, I'm going to try to approximate the area from within. I don't get to use this, so there's going to have 0 height. But here I have this big chunk that I can use. Okay. This dips. Okay. And then here I get to use this chunk also. This is step 1. So you see, at step 1 already, I'm sort of taking different parts of the graph underneath, or of the shape underneath the graph. At step 2, I have the green. Now I'm going to chop this into two pieces and this into 2 pieces. Like this, and like this. Again, I look at sublevel sets. Like so. Okay, and there's this. So now, again, I can't use this piece, but here I have the smaller rectangle that I can add. I have this rectangle I can add. And I have this rectangle I can add. Okay. In the 3rd step, I'm going to go one more layer. Chop, 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 chop. Again, there's a very small rectangle I can use here. Take it. This part I can take. Here's a relatively larger chunk I can take. I can take this part, I can take this part, and this right here. Now, this function f is continuous, and when your function is continuous, you should typically expect, no matter what the integration theory is, insofar it is like intuitive enough, you should end up getting the same thing. And for continuous functions, this procedure is going to converge to the same number as this procedure. Okay? But it turns out, And this is where things start getting complicated with integral calculus. Once you desire to be able to integrate reasonable functions, it turns out that there are also a lot of more pathological functions that you end up declaring to be integrable. And so Riemann integrable functions end up being a lot more restricted compared to Lebesgue integrable functions. Even though for both of these paradigms, continuous functions are integrable. Okay? So there are many other functions beyond continuous functions for integral calculus. Any comments or questions so far? Now, these pictures, I hope, give you some idea as to how these differ. In reality, though, when you start looking into the technicalities, the flavors are very different. Because it turns out to do this Lebesgue paradigm, well, you need to be able to really understand these sublevel sets. In the case of continuous functions, sublevel sets were just a bunch of intervals. But in the general case, the sublevel sets end up being like a nightmare. Okay? On the other hand, for Riemann integrals, it's slightly more reasonable. And indeed, from the perspective of the Lebesgue paradigm, what you start with is, well, you first sort of think about what it means to be able to take the length or even take the volume, say, of a sublevel set. And you sort of like spend a lot of time. Things get like rather technical. And indeed, those of you who are going to go to grad school, the first class at the graduate level, first analysis class, is essentially this measure theory, the sort of theoretical underpinnings of Lebesgue paradigm. So you forget everything about like intervals, whatever, and then you define axiomatically what it means for a set to have some notion of a volume. And you call that volume a measure. It has to satisfy certain properties and so on. So we're not going to do this Lebesgue paradigm. We're not going to develop it any further. Instead, we're going to focus only on the Riemannian paradigm. Now I'm going to introduce some more details about this Riemannian paradigm. And in fact, I'll try to draw this table. Within the Riemannian paradigm, there's a couple different sort of integration theories, but the three that we're going to be interested in are, well, the Riemannian theory, Lebesgue theory, and Henstock-Kurzweil theory. So, Riemann integration theory, Lebesgue integration theory, and Henstock-Kurzweil. Henstock-Kurzweil. integration theory. Okay. So these are not paradigms, these are integration theories. I'm telling you, within the Riemannian paradigm, we're going to have 3 distinct integration theories. Most of our time are going to be spent on these 2. How about this? Well, it turns out that somehow using this partitioning or chopping the domain into pieces, it turns out that you can still, surprisingly, emulate this paradigm. On the other hand, too, from the Lebesgue paradigm, you can talk about this, meaning starting from this paradigm, you can emulate that. And so, for instance, from the Lebesgue paradigm, it turns out that a Riemann integrable function is nothing but a function that is continuous except on a set of 0 measure, whatever that means. So Riemann integrable function is a function that is continuous except on a set of 0 Lebesgue measure. I'll add one more thing here. Those of you who are going to take 30-20, you're going to sort of see one version of this Lebesgue paradigm. You're going to reinterpret this Riemann integration from this perspective. And you're going to say, oh, Riemann integration is nothing but integration with respect to what is called the Jordan measure. Or Jordan content, I should say. So 30-20, the multivariable sequel. Riemann integrability is the same thing as integrable with respect to Jordan content. So one final thing I want to say is that we're using a couple different sources at this stage. And the terminology might get confusing because in different books, they sort of talk about different, they sort of take different notions of integration as sort of the main thing. So in our Taylor textbook, when they're talking about integrability, they mean Riemann integrability. So in Taylor. On the other hand, so integrable in Taylor, and if you look at the notes of Terence Tao too, this is also the same. But I believe Terence Tao is explicit. And in Tao, in the Tao notes. On the other hand, if you look at the Fonda textbook, what Fonda calls integrable is really Henstock-Kurzweil integrable. So integrable in Fonda. And again, the notes that we're going to use is on Canvas. And then in Fonda, for instance, Fonda calls Riemann integrable, R integrable, and Lebesgue integrable, L integrable. Okay. So these are sort of general comments. like I said, we're not going to develop this Lebesgue paradigm. This is grad school, if you want, or 5,000 level analysis. It's a beautiful subject. I really like it, but we're going to focus on this. Again, I told you the Lebesgue paradigm is the industry standard, both for pure math and a lot of applications, stochastic processes, statistical mechanics, signal processing. It's all based on this. Riemannian paradigm is somewhat more limited, but the fact that there is this Henstock-Kurzweil integral, it does seem to be making a comeback in a sense. Okay. So, any comments or questions about sort of this horizon so far? Yeah, I should mention, I told you for Wiener integrals or path integrals, the standard method was to try to use the Lebesgue paradigm, but the past 20, 30 years, people have been trying to adapt this Riemannian paradigm to make sense of these infinite dimensional integrals that physicists require. And so it seems there's some hope in that regard, but I'm not an expert in that field, so I wouldn't be able to say any more than that. Now, let's focus on this. In the textbook, in either one of these textbooks, the way they define Riemann integrability is rather more complicated. We're going to take the fastest way to define Riemann integrals and Riemann integrability, following Turnstau's notes. We're just going to take this picture I drew and try to make that more rigorous, essentially. And so for that, we need to define certain classes of functions, namely step functions. Until further notice, I is a closed and bounded interval. Do I need it? Well, I don't need it, so I'm just going to take I an interval, actually. And I'm just going to give it a definition. Let I be an interval. A step function on I is a certain type of a function. Step function on I is a function which I'm going to denote by sigma because it's step, taking real values such that, well, it satisfies two properties. First, I want this function to be like a very simple function. If this is my interval, essentially I want something like this. So first, I want sigma to take finite many values. In other words, I want the image of sigma to be a finite set. So image of sigma is finite. So sigma takes finite many values. And each level set of sigma is an interval. So for any y in the image, the level set, sigma to the minus 1 of y, remember this is the set of all those x's in I such that sigma of x equals y, I want this to be an interval. Each level set is an interval. In principle, this interval could be just a point, of course, because the definition of an interval is that it's a subset that contains any point in between any 2 points it contains. But this is the definition. Okay. So let's give an example. So for instance, if I were to take I to be 0, 1, I can think of this function. Say like this, and then there's a jump. Then it's like this. Say this is closed, and then this is open. And then let's say I have here this also. That's an example of a step function. And so if you want numbers, this is 1, this is 1/2, this is 1/4, this is 3/4, this is 1/2, this is 1. So sigma goes from I to R, takes x, and sends it to, well, I need to write down the definitions. I have 4 pieces, so I need to be careful with that. 0, x, 1/4, 1/4, x. If x is 1/4, if x is like this, 1/2 to 3/4, and then 3/4 x1. Okay, here it is 0. When x is 1/4, it is 1. When x is in between these two, it is 1/2. When x is here, it is also 0. When x is here, it is 1. Okay? That's an example of a step function. As you see, it takes exactly 3 distinct values. The image is a finite set, 0, 1/2, 1. And each level set, maybe I should have said, is a finite union of intervals. Is the union of finite many intervals. Is the union of finite many intervals. Okay. Okay. Good. If you remember the picture of the Riemannian paradigm, or in fact also the Lebesgue paradigm, I was just approximating the so-called integral, or what I wanted to be the integral of f in terms of, well, integrals of things like this. So let's say for sigma, a step function well, if I had a picture like this, how can I associate to it a number that kind of works like an integral? Well, I would just take the total area of the rectangles underneath. Okay? And so I'm going to try to formalize that. One can take as the integral for sigma, a step function on a closed and bounded interval, because otherwise there's an issue. Oop. On a compact interval, one can take as its integral the real number well, what do I need to do? Each height, which I know finitely many, gives me one of these heights of one of the finitely many rectangles. And all I need to do is to multiply the corresponding, multiply that height with the corresponding width. And so I would add over all heights y times, let's say j, in the p-image, an interval, the length of j. Okay. So that's a good proxy for an integral. What is happening here? I'm adding over a finite set. I take heights attained by my sigma. There are finitely many. By definition, image is finite. It's a finite sum. This is giving me the height information. And once I fix a height, and if I were to look at the level set, again, by definition, this is the union of finitely many intervals. For each interval, I can look at the length of that interval. Okay. So maybe here this is like 1 over 4, 1 over 4. And so I would multiply the width together with the height to get the area. And if I add all of these up, that's a good candidate for the integral of sigma. Okay. We're out of time. Essentially, we're going to take this and keep pushing. Okay. Thank you. Tomorrow's Valentine's Day, so happy Valentine's. And Monday we have break. We're celebrating President Washington's birthday, so we don't have class. We're going to be back on Tuesday.